So this one starts with the flip-flop, the latch. So this is a latch, not a flip-flop. Why is that? But flip-flop, you have that structure as well. Flip-flop is just adding a clock to it. It's not being clocked. That's why it's a latch. You don't have a clock. Okay, so it's a latch. So R means reset, S means set. So which means if you turn on S, it should set Q. Okay, Q is the output, and Q bar is the inverse of the output. Just keep in mind. So if you turn on R, you are resetting Q. That's just by definition. Okay, it can be a NOR gate, it can be a NAND gate, can be different types of gates here as a latch in the latch. But as long as you figure out which one's S, which one's R, it must be like when S is on, you set Q. When R is on, you reset Q. And you don't want to keep both of them. So for this NOR gate structure, you don't want to use 1, 1 here. It's unknown or it's unused. But you can do 0, 0, which is a memory input, which will store the previous value. Okay, so why we don't want to use 1, 1? What's the problem of it? Is this going to just fry the chip? Or if I put a 1, 1 here for SNR, what's going to happen? Look at the circuit. What's going to happen? Just let me know what's going to. So we don't want to just memorize it, right? So it's unused. We will never use it. But if you use it, what's going to happen? So you have learned the structure of the CMOS, right? You know what's inside. You don't have to look at this feedback, because the NOR gate, if you put a 1 in here, it kills it. You couldn't, whatever the data is here is going to get a 0 for you. Okay, same thing for this one. Doesn't matter what's the feedback. If you got a 1, you got a 0. You got a 1, you got a 0. Is there anything wrong with it? We just don't use it that way because we labeled as Q and Q bar, which means we expect this is the inverse of this one. We don't want to have the same value. It's just not useful. The reason we need a latch and we need a Q bar here is we're going to use a Q bar, which is the inverse of Q. But if you give a 1, 1, you're getting 0, 0. It's just not useful at all. But it's not going to fry anything. It's not going to, damage anything. It's just an unused input. Okay. So if you give a 0, 0, then it's going to be a memory. And why is that? Because 0 is not going to change anything for the OR gate or NOR gate. Right? It can be ignored. It's going to be determined by the other one. Okay. So in here, we never use 1, 1, but we can use 0, 0 or 0, 1 or 1, 0. Depends on the purpose of the input, what you want to do for the output. And how to model it in Verilog. Keep in mind, some of the circuits may be not accurate. I think I made the snapshots from the textbook. When I was looking at it 1 hour ago, I just found another circuit just scrolling down. Doesn't match the code, but this one matches. Okay, so when you code it up, we're going to implement this latch in Verilog. How do we do it? Because that's the purpose, right? We don't want to build it. Can you still try to recall how you built this kind of latch in digital? You took digital and logic, right? You can build it in LTSpice. So I have to build every transition and put them together and wire it up. But you could just look at Verilog. Just type, 1 minute. And it's going to synthesize a little latch into the IPGA chip. That's why IPGA becomes so popular. So simple. And in LTSpice, you run the simulation and you have to put in cadence and send it to TSMC, $6,000 to make a chip for you, which has a little latch on it. But now it's just coded up and then it's going to make a little latch on IPGA. So how do we do that? It's a module and has inputs, outputs, and I have to assign initial values to them. No, they are assigned using this non-blocking assignment. So that's why we use a register type, and always. So this is a block. This is the chip of the latch. We're not doing the test bench yet. So this is the chip. So always add SOR. Okay. So these are the sensitive lists or the sensitive list. If S and R are not changing, do we need to do anything? No, we just keep the initial value. So this is legit, right? So always add whenever they change. Then I'm gonna assign new values to Qn, Qn. The real circuit being synthesized in the IPGA chip is not necessarily this one. Keep in mind, it's not this. It's not this schematic. It's doing the same job. There will be more gates, more circuits in there. It's doing the same job, just following the commands being set by the user. Right? Whenever SOR changes, if S is 1, right? If S, it didn't say that, but if S is 1, then I'm going to assign 1, 0 to Q and Q1. Does that make sense? Because when S is 1, I'm on a set Q. So that's why Q is being set. Right? This little 1 here. Else, if R is 1, I'm going to reset Q. But at the same time, I have to invert Q, or I have the Q1 as the inverse of Q. That makes sense? Yeah. Is this doing whatever the truth table is telling you to do? It does these two, right? What about memory? What about this? Unused. We're assuming unused combination of the inputs will never happen, right? But what if it happens? Yeah, this is weird. I think it's considering not having 1-1 happen at all, because it matches both, right? S is 1, R is 1. It happens at the same time. But I think it's gonna match this one first. No, actually it's being synthesized to the circuit at the same time. So it matches both. And I don't think it's gonna work. So not considered, because we assume that this won't happen at all. Okay. So what about 0, 0? If you look at the code, here's the condition here. If you got 0, 0, it will do nothing. It's a memory. So it's not changing anything. Okay. It triggers, does it trigger the always sensitive list if some bit flips to 0, 0 from 0, 1 to 0, 0? Is it going to trigger this one? Yes, because it changes, right? But get into the block, none of the statement matches the change. It will do nothing. So it's a memory. And what about the test bench? So I put the module and the test bench in the same .v file. You can see that I have a simulation. I'm using initial beginning and delay by 10 nanoseconds for each. So I had a 1, 0 at the very beginning, and then I changed it to 0, 1. If you want to make a 0, 0 there, which will be good actually, you want to see if it's going to memorize it. Okay. You can add 1 to it and put it in the report. It's a very simple change in there. You can see it works whenever S is 1, you set it, right? When R is 1, you reset it. And here's a flip-flop. It's different from the latch because I'm clocking it. It's still the same latch structure, but I'm adding 2 AND gates and a clock signal to the input of AND gates. So I think this is the one that the truth table does not match with the code, I think. Let's take a look at it. It doesn't match the truth table because if you give 0, 0 to S and R, we are assuming clock is always 1, right? Otherwise, these 2 AND gates are disabled. So I have to put a clock 1 here, right? Clock is 1, see? So when clock is 1, assuming these 2 AND gates are activated, and if I have 0, 0 for R and S, 0, 0 for R and S, what's going to happen? No. I know the truth table says that, right? But the circuit doesn't match. I told you, right? So let's take a look at it, see if that's true. If you think that's wrong, just let me know. Okay, we can talk about it. So if S and R are zeros, right? So you are having what? 0. So it is a memory. That's you're right. I don't know why I look at that, in a different way. So whenever R and S are ones, what's gonna happen? Yeah, both 1 at the same time. It's not, and this is 1 as well, right? So you are getting 1, 1 here. So it's not being used. Okay, so this matches, right? No problem with the truth table and circuit. If you have S, if S is 1, R is 0, which is the normal input, one of the two combinations. So S is 1, R is 0, we are setting or resetting Q? Setting. Okay, let's see. If S is 0, you got a 0 here, right? If S is 1, because clock is 1, you're getting 1 here. And by looking at the latch here, right, it says SR, right? So setting. Whenever S is 1, it's setting it. But you can also look at just routing the signals back and forth to verify it. We don't want to waste time on that. But we know that it's setting, so this is correct. So S should be here, right, for this SR latch, SR flip-flop. But keep in mind, this is not only schematic for SR flip-flop. I think the ones we used are just pure NAND gates in digital. Either way, it's just changing the location of the S and Rs, just doing the same job. Okay. So now let's see how we model it. Since we just added the clock, so both clock and S has to be 1, because clock has to enable the AND gates, and S has to be 1 in order to set it. And then I set it, right, because I put a 1 here for Q. I set it. Otherwise, if clock and R are both 1s, then I'm going to reset it. If the condition does not match these two, which means its clock is 0, for example, it's the memory, okay? Or if you got a 0 zeros, if you have 0 for one of S and R, this wouldn't match, right? What's gonna happen then? If you have both of S and R are zeros, what's gonna happen? So check this one doesn't match, check this one doesn't match as well. Doesn't matter what clock is, right? It just doesn't match both of them, so it's gonna be a memory. So it works. And I think this one verifies the memory one. You can see I got a 0, 0 here, right? 0, 0, 1, which is SR and R zeros. So in that case, when you are looking at the diagram, you can see if it's memorizing things, right? See here, I got a 0, 0 for S and R, right? Your Q is not changing. Q is memory. It's following the previous Q, okay? Yeah, just do the similar analysis for the rest of the timing diagram to verify it, see if it's doing the SR flip-flop's job. And this is a D flip-flop. It's passing D to Q. Keep in mind, Q is the output. Q bar is the inverse of the output. So D has to be sent to Q, not Q bar. Okay, so data flip-flop or D flip-flop is gonna send D to Q. And when you are programming Verilog to implement that functionality, you don't have to think about the circuit. Forget about circuit. That's why I told you guys, someone worked in Qualcomm getting like $160,000. They never understand what is CMOS, how the transistor works, how the circuit works. They just do the behavioral. Just do the behavioral. I just need, whenever this one triggers, I need this one to be set. Just put it up. You don't have to think about circuit. Truth table. And see, D flip-flop, super simple. Check out the code. D or C, if D or C changes, if C is enabled, if clock is on, I'm going to send D to Q and D bar to Q bar. So what's the difference of the D flip-flop compared to the SR flip-flop?
We don't have to set.
Because one of the inputs is always the inverse of the other one. So it avoids what? Memory and the unused one, right? But how do you do a memory though? How do you want to memorize things? You just put clock to 0. Okay, so that's why when clock 0, it's Q previous. Doesn't matter what is D, because the clock 0 is going to kill these two AND gates and give you zeros here. Right? It's going to work. And this is edge triggered or level triggered, and why? Did we talk about edges at all when we were analyzing this circuit? No, it's not. It's not edge. It's level triggered. When C is 0, it's a level. It's a memory. When C is 1, it's enabled. So when the clock is at a certain level, it determines the behavior of the circuit. It's not just looking at the edge. Because how do you differentiate it? Is a Q only triggered? So the change of the Q only triggered by the edge, or is going to trigger by level? For here, it's triggered by level. So when clock is on, if D changes, Q is going to change, which is bad. Does that make sense? Because these are just logic gates. As long as clock is enabled, so if D changes, definitely Q is going to change, right? It's not controlled. It's bad. What you want is, I mean, the better one is you so you only trigger that change of Q at the edge. So if D changes later on after the edge, Q is not being changed anymore. So you can do a really accurate sampling. So you're sampling the data by the edge. Yeah, definitely the level trigger will be used somewhere else as well, but I think rarely being used. So we need a edge trigger. So we'll see the difference. Let's look at the edge triggered. So that's the edge triggered. Why is this one, from circuit analysis point of view, why is this is different from the previous one? Why is this edge trigger instead of level triggered? You have two stages. You have two stages of the same D flip-flop. So this D flip-flop is a level triggered. So the D flip-flop is just so, right? And you got two stages. So whenever clock enables the first one, the second one is disabled. So it's edge triggered and data being stored in the middle. And another edge comes, it's going to send the data to here. But at the same time, it's going to disable here. So whatever D changes, just won't be sent to here anymore. Or won't be sent to, that's right, won't be even sent to here. So don't mention here, okay? No, just left alone here. So that's why it's edge triggered. But again, when you are coding up in Verilog, you don't need to design the circuit. It's just getting very simple. You just need to add pause edge. The Verilog is going to synthesize that for you, right? So you tell them to do that edge trigger. So pause edge, and also this adds a little clear function, the reset, but it's not showing up here. But just need to know that you can do it or you don't have to do it. So this will just reset everything. So pause edge clock, whenever it's edge, pause edge or rising edge of the clock, you do the following. Otherwise, see if you get a negative edge of the clear, then you can reset everything. So whenever you get into the block, if clear is 0, then you reset it. So see, Q got a 0, Q bar got a 1, you reset it. Otherwise, it's a normal operation. D send to Q, right? No problem. The D flip-flop, D send to Q. But only at the edge. That's how you can make sure it's edge trigger, not level trigger. So this is going to synthesize a different circuit than this one, but it's just show you the concept of the circuit, but in whatever is being implemented physically in IPGA will be different. And I don't know what that looks like, and you don't have to know as well. I think this is a kind of secret of either Xilinx or Ultra, how they synthesize or implement the logic into circuits. I think it's IP. They are not going to disclose it. And here is a D flip-flops module, and here's a test bench. Okay, so I designed a loop, for loop to form a clock, right? And I delayed it. That's why you can see the delayed and flipped clock signals, so you can form a rising edge. Okay, so in the rising edge, I just randomly pick up a range of numbers, which one I want to put a 1 for D, and for the rest I clear it, so I can run or verify the different functionalities of the design. You don't have to have 3 and 10 exactly, right? You don't have to have 20 here exactly. It's just a number or range that I can verify. So for example, after 50, whenever it is 15, I reset everything. I think whenever I is here, I couldn't show the numbers here, but whenever it's 15, I think it's being reset. See, Q is being reset. But whenever it's larger than 10 and smaller than larger than 3 and smaller than 10, I put a 1 to D. That's why Q should duplicate D. So it's so when I is larger than 3 after this one, right? See if D is being copied to Q. Q, D at the rising edge, and Q, D at rising edge, and trigger it, Q, D and Q. So see Q here, the same as D here, until it's being reset. Okay, I've just talk about this really quickly, but you will either rewatch the video or just trying to look at the waveform by yourself, try to understand it. Edge triggered JK flip-flop, and you can make a T flip-flop by using a JK flip-flop. Let's see, how do we model it? So edge triggered when clear is 0, it's 0 active, that's why we reset it. Otherwise, for JK, the combinations, keep in mind in JK flip-flop, we always send J to Q. So for JK flip-flop, we send J to Q. See, when JK is 0, 1, Q is 0. See, J, Q are the same. J, Q. However, when you have JK both tied to VDD, like 1, 1, it's a T flip-flop. It's a toggle flip-flop. So whenever clock arrives, it toggles the output. And we use T flip-flop to form counters in the ADC design in digital. But just keep in mind, just let you know that T flip-flop is a toggle flip-flop, but you have to have the input of the JK to be tied to VDD at the same time. So when clock arrives, each time it flips the output. It's just a property of the T flip-flop. It's one of the different types of flip-flops like being broadly used. So whenever it's 1, 1, when clock arrives, right? Pause edge, get into here, and it's 1, 1. You put a Q1 to Q and Q to Q1. That's how you can flip it. It's toggling. It's toggling the output. Does that make sense? The Q0 is Q right now. It's toggling. So now just followed by T flip-flop only. So it's not the JK and it has a T flip-flop in the middle. It's just totally just a toggle flip-flop. It's easier. So 0 will not toggle it. But 1, when t is 1, it's going to toggle it whenever the rising edge arrives. So see how we model it. Whenever the rising edge arrives, you got into here, and Q will XOR with T. Let's see if that makes sense. Because T can be 1, can be 0. You can definitely do an if statement, right? If T is 0, then Q bar will be sent to Q, right? But this one is just the easier way to do it, right? Remember the XOR logic? If T is 0, right? For example, T right now is 0, okay? If T is 0, and if Q is 0 as well, you're getting a 0. And then in that case, Q equals to the output, or the final Q. Yeah. If T is 0, again, now we're talking about when T is 0, so we're not toggling the output. And then Q is 1. So XOR logic, Q and T are different, so the output has to be 1. Okay, and Q, remember, is 1, and the output is also 1, so it's not changing anything. That's why it's a memory. It's this one. So when T is 0, it's a memory. But when T is 1, if you XOR something, if you XOR 1, use something and XOR with 1, you are inverting it. So that's why it's flipping it. We can verify by ourselves, right? So if T is 1, if you got a 1 here, then the result is 0, because 1 and 1 are the same. If T is 1, you got a 0 here, the result is 1, right? If T is 0, Q is 0, you got a 0. Register is just D flip-flops. It's parallel in, parallel out. See? It's getting to D and getting to Q at the same time. So it's parallel in, parallel out. P in, PI, PO. Register. So when clock arrives, it sends all the D's to Q. It's like a latch, right, or a memory. It just register all the data at D to Q. Just register all the things to the register. In memory, there's no tasks related to it, so I don't want to go through it. You don't have to worry. Just ignore this one, okay? It's not useful. For ROM, it's a read-only memory. So this is something you have to use for a lot of really advanced applications down the road in the semester. That's what I talk about at the beginning of the class. Is starting getting fun because we're doing memory stuff. And for the VGA project, you put you can convert a image, whatever image you can make, snapshots or something, and you can convert it into a memory file, and then send it to and program it into the FPGA and send it through VGA to a monitor. So you can do it by yourself. Just let the FPGA send everything through VGA to the monitor. So for the dynamic ones, the game Max and David made, right? It's a similar principle. It's just all the pixel data being saved in the memory file and being sent to the monitor dynamically through VGA. So as the first memory file we are going to deal with, how do we do it? It's just a memory, it's just a Verilog file. So it's ROM, right? ROM, that's a Verilog file. So the ROM is a memory. It's like a chip or digital block. It has an 8-bit address bus and has a data output. So it's like you put an address at the input, then it's gonna take out the data at the address and send it to the output, which is data. So address, data, address, like a decoder, right? I put this address in, so that address, they find out that address line and send out the data to the output. So this is how you model it in Verilog. It can be very straightforward because we are programming it instead of designing the circuits. It can be like 1,000 times faster compared to laying out a ROM by hand. So we had the two enable pins. It's the chip enable and read enable. You don't have to worry about that. You have to put a one for both in order to make it work. And the next one is a memory. That's a memory block. Okay, what does that mean? The register type of memory, which is from 7 to 0 and has this much. What does that mean? So what does this mean? 7 to 0. That's a memory block, okay? That's a memory self. So 7 to 0 means it's a 8-bit memory, and 0 to 255, which means it's at the length of the memory. So each memory block is 8-bit, right? And I have how many of them? 256. So 256, what? 256 what? MB or 256 bits or 256 words? No. Huh? So 8-bit words are bytes. Yeah, so 256 bytes, right? 8-bit is a byte. So it's 256 bytes. So if you write it down, it's going to be 256 B, capitalize the B. This was 40 years old memory, or maybe longer than that. 256 bytes. It's not 256 MB, megabytes. It's not, right? It's 256 bytes, right? And then if the address, which is the input, right? It's 8-bit input. So first, this has to be 1. Has to be enabled. Chip enable, read enable has to be 1 for both in order to enable this one, right? Otherwise, just output 0. It's not enabled, just output 0. So the memory is sending a 0 to the output. But now we are just looking at the ones which is when it's active. So the memory block has an address in there, so it's choosing one of the 256 memory blocks and send it to where? To data. That's the output of the memory file. Make sense? So as long as you enable it, it is a combinational block. It's not a like behavioral, because when the address arrives, the chip, you got a data there. So address here, data out. Okay, you don't need a clock. There's no clock. Keep in mind, it's a combinational block, combinational logic. And so now we know that this is a circuit of the memory, but we need to define the data in the memory block. So what are these data in the block? You have to read a memory file. So the memory file, you can create it by yourself by text editor, but change the extension to .mem. Okay, and this $ and read mem b, you couldn't change it. That's a keyword. It's going to read this memory file, and you are telling Verilog this is a binary memory file. So the data in there, the 0, every 0 here is a 1-bit 0. It's not a 4-bit 0 like hex. Okay, so I have to specify that it's a binary memory file. That's how you read it in. All right, so here's how it looks. I have to create it. I don't know if there's something I can download it. So there are not too many. If you copy and paste, right, you generate the 4 and you copy 4 to 8 and you copy 8 to 16, you can get it done in 15 seconds. And you change one of the bits or two or three of the bits in there, just type press R on the keyboard or just replace it. You can do it really quickly. And it doesn't matter if it's repeating, you can repeat it. So if you make 4 of them are different and then you keep copy and paste, you can make like many duplicates of the four lines. And so you can make this one really quickly in Vim. And here's a test bench. Okay, so the memory's circuit, and that's the memory file, memory data. Okay, and this is the memory's test bench, which will wrap up both, put both in there. And you can see that what I have here is initially I have enables are zeros, it's not enabling, address 0, starting from the very top, and monitor. So monitor defines how you want to display this data in your final waveform. Hex form, binary form, see? So that's how I can change the look of the waveform. And now I'm making a for loop to, so I is the address. I'm changing I from 0 to 255. So I keep incrementing that address by 1, so it's taking out every single data from every single address from the memory. Okay, you can just simply change the address, because remember, there's no clock. The address line is being physically shorted to the address line of the ROM memory block. If you change the memory, if you change the address, it's going to output data from that address automatically. Okay. When you run a simulation, don't forget to add it as a design source, I think. But if you have a different option, like adding a memory source or something, you can try it as well. But I think if I put a design source, I add it as a design source. Just right click and add sources, so you can see the man file will be automatically placed in this memory file Dropbox. And then you run the simulation, it's going to show the data here. You can see these are the data being displayed in the hex format. Okay, 8-bit, right? Hex, 2 bits of hex is 8-bit, it's 1 byte. You can verify from here. And you can so there's a following task is to modify the binary data file into hex. So these are hex numbers, even though it's 1, 2, 3, 4, but these are hex numbers. So 1 is 0001, actually. 2 is 0002. What? Testing you. Trap. So 2 is 00. No, it's a hex number, right?
No, I thought it was converting it.
Wait. It's a hex number 0010.
Oh yeah, in binary.
Yeah, in binary. Yeah. So 3 is 0011, and this is 0100, right? So you have how many bits in each row? How many bits, binary bits in each row? 16, 4 by 4, right? Okay, but I have to specify that. I have to tell Verilog these are hex numbers. It's the only thing I have to change. Read mem h. Okay, that's how to do it. And no significant differences in the rest. But another thing you need to know is you can use the separators. Okay, so the separators in the data file, because these are just text editors of text files. And you can use space, tab, new line as the separators for the different data. It doesn't have to be new lines like these ones. I use the new lines, right? But if you place them just one after each other by a space, it's going to work as well. So each 4 hex digits, it's going to be 1 memory block. Keep in mind, even you put them in 1 row.
So if you have 1 space something and then a tab below it, is it going to read across first, or is it going to read down first?
I think left to right and then to the next.
Okay.
Good question though. See this one? It's a hex. It's a hex number, data, right? Or data memory file in hex. So how many memory blocks are in there? No, how many memory blocks? Yeah, 16. Okay, so the length of the memory file is 16. So how many bits are in each row, in each memory block? No, how many bits? 8. 2 hex digits are 8 bits, right? So it's each memory block, each row in a block is a byte. So that's why I put a 720 as the data, right? And do I really need 1620 bits for the address? How many bits do I need for the address to able to take out every single data from the memory file? Hmm? How many rows do I have in here again? 16. So how many bits do I have to differentiate the 16 different lines? Hmm? 4. I just need a 4-bit address. I don't need a 16. So 16 is gonna. So if I do a 16, what's the size of the memory? So the 16, huge. I don't need to do that. I don't need the 4 bits, but I still did that, right? Just to let you know, you don't have to. I need a H here because it's a hex number, right? The hex format. Data are in hex. That's why I need an H, read map H. And you just play around with it in order to verify it in a simulation. What about this one? I didn't use new lines. I just used space. And it's a battery file. 3-bit battery file. How many do I have? 6. I only have 6 in there. I only need 3 bits for the map for the address, but I put 6 bits here. It's just more than I need. Make sense? And so this is how you do it by coding it up. It's a ROM, but also you should know that you can use the IP blocks in Vivado. So Vivado provides IPs. So what are IPs? Did you create IPs here by yourself?
Yeah.
You did. All the modules are IPs. It's like a chip. It's intellectual property. It's easy, but it's your intellectual property. It's a little chip. And if you send this module to someone else, they can reuse it in their project easily because it's transferable and it's an IP. And you can imagine that the IP blocks being provided by Vivado, it's the same thing, just a block, a chip with input and outputs, nothing else. It's more complicated. Keep in mind, every single module has inputs, outputs, right? So the inputs, outputs, if you draw a little square around the inputs, outputs, it looks like a chip. It's a chip. So this memory is a chip. You don't have to program it. You don't have to mess with it. It's just already a module. You just need to declare it, right, and use it. So in your test bench, you just declare it in there, like UUT something, right, and then use it. So this memory file that I can configure it in Vivado and just follow the instructions exactly, and you can see it's pretty big memory. And the memory chip is just the memory chip. It doesn't have data yet. Make sense? So when I went through the ROM file here, the ROM file is a ROM file. It not necessarily have the data. If you don't put the data here, it doesn't have any data in there, just empty blocks. So same thing for this one. You create a block, it's just a digital circuits, like the decoders and the enable pins, right? It's just these kind of things in the ROM. But you have to add something to it, like this one. So that's a data file. And I think I have a link for you guys to download it. It's here, right? Just download it and upload it, and then load it to your Verilog project or load it to here. You browse it and find it and load it here. I think this is the image. I forgot what image that is. But for the simulation, you are not able to see anything. Could you see an image? No, you couldn't see the image by doing this. It's just the data of every single bit. It shows the numbers of each pixel, but won't combine them together and make it visible image. Okay. Your brain actually converts into an image. Your brain receives the light intensities of the pixels and convert into the image. But this is different from your brain. This is not able to. Your brain cannot resolve it. Cannot just understand the one and zeros and change it to an image. Right? Is that true?
Well, we'll see.
No, you look at the map with all the pixels in there in the map with different intensities, and then your brain understands it's an image, it's a picture. But if you have all the waveforms, they also show the intensity of the pixels in a bytes format. Your brain cannot understand it, show image in your brain. So this little task will not show you an image. It just shows the waveforms. So how to show image? There's something you have to work on. I think I didn't show you everything about it. Have to modify or add new things to the test bench to make it work. Not providing all the solutions, but based on the experience from last semester, it's totally doable. I didn't see any issues with it. Just following the examples from the earlier of the tutorial to finish this one. Okay. Again, so how do you show an image from the data? So if you how to convert into image? You have the data for each pixel, right? It's a data file being saved in a .coe file, and you load it in Vivado, and if you load it in Vivado, you open it up, it's going to be all different rows of numbers, binary numbers for each pixel. So how do you show the image out of that data? What are the ways to do it? In different technologies, it's an open topic. I'm not saying just FPGA, but for example, if you are doing FPGA, how to show it? No, it's show the waveforms. You couldn't see the image. There's data, right? How do you show image? Using the monitor.
Yeah.
So the monitor can show image, right? How to do that? RGB, or you have to communicate with the monitor. If you use the VGA, you need a VGA digital block and send the data to VGA sequentially, and eventually let the VGA send the data to the monitor to assign the pixels to each picture so you can see it. That's one of the ways to do it. Another way is you can convert it into, you just save it as a data file, and because you're using a computer now, you have a computer, so you have to send it to another computer. You have a computer with a monitor on it, and you have the data file. MATLAB, Python, just plot it, right? It's a matrix. It's 1 by 256. It's a vector or matrix. Just show the data, just plot it. So I think the functions in MATLAB or Python is able to plot it in your monitor. And just some ideas. Make sure you understand everything. Any questions?
Yeah, can we go back to the memory, the address? I'm kind of still confused about how you're getting the
First one.
Yeah.
Okay. How to get what?
Like, so we have a certain, like the 3-bit data. How do you know how long the address needs to be from that?
Oh, because you just need like for example, the binary one, like this one, okay?
Yeah.
You only have 4 different rows, and you just need the 4 different numbers to differentiate in between of them. You know what I mean? It doesn't have to be how many data are in there.
Okay.
The length of the memory file.
Okay.
So the way how that works is the address doesn't have to be 0, 1, 2, 3. It doesn't have to be that. But it's just a better way to use it, because when you increment it, you can directly take out every single one just by incrementing that address by 1, right? But it's just a decoder. It's a decoder. You can design the decoder's logic to understand whatever address it is. It can be 000, for example, as the first address, but you can change it to like 111 as the first one. It's okay. You just need to change the code. So look at the code here. If you do that, you need to, whenever you receive a 111, you just send mam, what's the name of that bracket? Square bracket. Square bracket. You put 0 in there. Does that make sense? When address is 111, it sounds odd, right? So when address is 111, I send the number 0 of the data in the list or memory to the output. But usually we don't do that, right? We usually just address 0, we send a 0. Address 111, we send a 1. But you can design the decoder circuit, or you don't have to think about circuit when you program in Verilog. Put 111 and output a mam 0. 110, I output a mam 1. It doesn't matter. So depends on the length of the memory. You just need that many of different numbers to differentiate each row. Because if you get the same number, it's an if statement, you show the same number, but it's sending out 2 different data, that's not going to work. So 1 address, 1 data, right? 1 address, 1 data. So if you have that many addresses, that many data, you need that many addresses.
So then going back over to the matrix block of data that we have.
Which one?
It keeps going down. A little bit lower. That one.
Yeah.
So if we had a 5 by 4, then we would want the address to be 2 to the 5th instead of 2 to the 4th.
That's right.
Okay.
Yes, 32 will be good enough for 25. 20.
Okay.
Yeah. Yeah. All right, and I believe it's reading left to right and top up and down, going down. So it's 1, 2, 3, 4, 5, 6, 7, like that. I believe, but you can verify here. See, A, B, C, D, E, F, 0, 1. A, B, C, D, E, F, 0, 1, right? And what's the next? E, F. E, F. Okay? All right, that's it. Okay, cool.